Chapter 1: Blockchain Basics. Blockchain is more than just a technology. It's a revolutionary approach to recording information and transactions in a way that is virtually impossible to alter, cheat, or hack. It is a digital ledger of transactions that is duplicated and distributed across the entire network of computer systems on the blockchain. Each block in the chain contains multiple transactions, and every new transaction that occurs is recorded in every participant's ledger across the globe. This system ensures that all records are kept consistent and accurate as the ledger updates itself every 10 minutes. The decentralization of blockchain is key to its security and robustness, making it extremely difficult for any single entity to gain control of the entire network or manipulate the data it contains. Chapter 2: The Anatomy of a Block. Each block in a blockchain carries a distinct composition that fortifies the security of the ledger. Primarily, a block contains a block header, which includes important data like the timestamp, a reference hash to the previous block, and a nonce, which is a cryptographic puzzle used by systems like proof of work. The block also stores transaction data, detailing each transaction's specifics such as sender, receiver, and amount. These blocks are linked in a chronological chain using hashes, cryptographic codes that secure the blocks and link each one to its predecessor. Altering any block's data would change its hash and require recalculating every subsequent block's hash, a task that is computationally prohibitive on large and active blockchains, thus ensuring the integrity of the blockchain's history. Chapter 3: Consensus Mechanisms. Blockchain's reliability hinges on its ability to achieve consensus among network nodes about the validity and order of transactions. This is accomplished through various consensus mechanisms that ensure agreement without a central authority. Proof of work, POW, is a method where miners solve computationally difficult puzzles to validate transactions and create new blocks. The first miner to solve the puzzle gets the right to add the block to the blockchain and is rewarded with cryptocurrency. Alternatively, proof of stake, POS, is a more energy-efficient consensus mechanism where validators are chosen to create new blocks based on the number of coins they hold and are willing to stake as collateral. These mechanisms prevent fraud and ensure that all copies of the distributed ledger are consistent, making blockchain a trusted and verifiable system. Chapter 4: Blockchain Security. Blockchain security architecture is one of its most lauded features, offering a robust defense against many types of cyber threats. This security is largely derived from its use of cryptographic hashing, a process where transaction data within each block is converted into a unique, fixed-size alphanumeric string, known as a hash. This hash function is designed to be a one-way operation, ensuring that the output does not reveal any information about the input, and any alteration to the input data will produce a completely different output. This characteristic is crucial for maintaining the integrity of the blockchain because each block not only contains its own hash, but also the hash of the previous block, creating a chain of dependency. If an attacker attempts to alter a transaction, the hash of the altered block will change, which will subsequently invalidate the hashes of all following blocks, thus alerting the system to the tampering. Additionally, blockchain uses public key infrastructure, PKI, to secure the data transmissions across its network, ensuring that only authorized users can access certain data on the blockchain. Chapter 5: Smart Contracts. Smart contracts represent a paradigm shift in how contracts are executed and enforced. These contracts are programmed to automatically carry out the terms of an agreement as soon as predetermined conditions are met, without the need for human intervention. For instance, a smart contract in an insurance blockchain could automatically process claims and release payments once the required evidence is submitted and verified. These contracts run on the blockchain, which means they benefit from the technology's security and immutability. This not only reduces the risk of fraud, but also significantly lowers the transaction costs associated with traditional contracts, which often require a great deal of manual processing, mediation, and enforcement. The decentralized nature of blockchain further ensures that smart contracts operate in a transparent environment, where all participants can see the outcome and the conditions under which the outcomes are triggered. Chapter 6: Challenges and Limitations. While blockchain presents numerous advantages, it is not without its challenges and limitations that may hinder its broader adoption. Scalability is one of the primary concerns, as traditional blockchains like Bitcoin can handle only a handful of transactions per second, compared to thousands processed by conventional financial systems like Visa. This limitation is due to the size of blocks and the interval at which they are created, which, while ensuring security, limit transaction throughput. Moreover, the proof-of-work mechanism, which secures transactions on networks like Bitcoin and Ethereum, consumes a significant amount of electrical energy, raising environmental concerns. Additionally, the regulatory landscape for blockchain technology is still evolving, with varying degrees of regulatory standards across different countries, creating uncertainty for businesses and investors. These regulatory challenges, coupled with the technology's complexity and the need for widespread technical understanding, pose barriers to the adoption of blockchain technology on a global scale.